Hey there, in this video we're going to look at an example virtual lab that we'll do by my recording the lab and then you doing the analysis, drawing conclusions, all of that sort of stuff. So in this walkthrough we're going to look at the stuff we need to do in a virtual lab report, and the lab I've come up with for today is to take this super ball, which is supposed to be super bouncy, drop it from 5 different specified heights that I've already chosen, and see what its rebound height is. And we'll do a comparison. The comparison is going to be between the height it's dropped from to the height it rebounds to. If it's super bouncy, it should get pretty close back up to where it was dropped from. If it's less bouncy, then it's not going to rebound up as high. So we're going to look at those 5 different drop heights. You could call those independent variables, and then we'll measure the rebound height. That's going to be the dependent variable. On the whiteboards behind me, which I've set up against the wall, I've marked out the 5 different heights that we're going to release the ball from. At the very top is the tallest height, which is 1.80 meters. The second highest height is 1.60 meters. The next height is further down below, 1.0 meters. Then we have 0.8 meters, and then at the very bottom, the lowest height is 0.5 meters, only half a meter. We'll drop the ball from each height and then look at the video to see exactly how far it bounced back up. So that you know the full setup, we have whiteboards all the way up the wall, up to the top there. We have 2 meter sticks taped together. They aren't overlapping. So you can see where I've marked the 1 meter mark right there. That's the end of the first meter stick. And then any measurements we see above that, this would be 1.2 meters because that's the 20 centimeter mark of the second meter stick. All the way up to there's 1.6 where I have that written. So that's the 60 centimeter mark on the second meter stick. And we're doing our first drop height at 1.8 meters. Alright, so let's drop from 1.8 and see what it rebounds to. Alright, from 1.8 meters, we're dropping in 3, 2, 1. Alright, our next drop height is going to be from 1.6 meters. I'm going to drop it from here in just a moment. See where it rebounds to from 1.6 meters. 3, 2, 1. Alright, our next drop height is just 1 meter. There's our 1 meter mark right there. 1 meter and 3, 2, 1. Our next drop height is 0.8 meters, right here. 3, 2, 1. And our last drop height is going to be from 0.5 meters. 3, 2, 1.
Now that we've seen the data that was taken from our video of the lab, we want to go through what components you should have in your lab report. Our example lab report guidelines are given here on the page that you see now. Starting from the top, you want to make sure that you have name, date, and the name of the lab at the top of your page, just like you do with the assessment questions. You can set up your paper, if you're writing everything, into 4 rows or quadrants, just like the assessment questions. You can complete your lab report digitally, entirely, or you could do it all by hand, or you could do a combination of digital and written work. Perhaps you want to do some of the components written and then just do your data table or graph digitally. 4 components to the lab report, just like there are 4 components to the assessment question rubric. Really, it starts at a 0 if you don't turn anything in, 60 if you turn something in, regardless of the quality of the work, and then each of the 4 components listed below, just like with the assessment question, brings you up to a 70, 80, 90, or 100. Let's look at those components real quick, and then we'll see how we can produce a lab report. The first component is the diagram, which gets you plus 10 points. Your diagram should just be a drawing or sketch, which you could do digitally if you wanted to, or just draw by hand, of the lab setup with labels for each thing in the diagram. It should include everything that you saw in the lab video, so it's every physical thing that's there, useful for doing the lab. The second component, which is worth another plus 10 points, would be the procedure. The procedure just needs to be in listed steps, 1, 2, 3, 4, etc. That includes what measurements are being taken, what measurement devices are being used to take those measurements, and then what units the measurements are being recorded in. We'll see an example of this in just a moment. The procedure needs to be in listed steps, 1, 2, 3, 4, etc., but they do not need to be in complete sentences. Third component, which is worth another plus 10 points, is the analysis component. You need to analyze, collect the data. The data could be in a table, and if the lab assignment requires you to do so, you should also produce a graph for that data. If you need to produce a graph for a lab, it needs to be properly titled, the axes need to be labeled and scaled appropriately, and you need to indicate a trend line for that data with an equation for that trend line if it exists. In later labs for the physics course, you might be required to linearize your data if it isn't linear already. That means if you produce a curvy graph, you need to make it linear, but we don't do that until later. An important thing about the analysis is, depending on what type of lab it is, you may only need a data table, or you might need a data table and a graph, or you might need to show just mathematically how you solved the problem from the collected data, if it's something like a challenge lab. So you need to make sure you read the instructions on the lab report assignment, and I will be very clear about what you need to include in the analysis portion. You can think the analysis component is like the mathematical or quantitative part. So in some labs you might just need a data table. In some labs you'll need a data table and a graph. In some labs you may not need either of those things, but you need instead to show what equations you're using and then the work in solving those equations to get the answer that addresses the question or the objective of the lab. So make sure you read the lab report instructions closely so you know exactly what you need to include in your analysis. For example, the first physics lab, where you're actually looking for the exit velocity or launch speed of a dart from a Nerf gun that's launched vertically. You don't need a data table or a graph for that lab. What you need to do in your analysis is show what equations you're using in order to find the launch speed. So there's an example of analysis. The fourth component, which is also plus 10 points, is the conclusion. But in order to get the points for the conclusion, you have to make sure you do the diagram, procedure, and analysis correctly first. Otherwise, you have no business drawing any conclusions. In the conclusion, it's kind of like the qualitative part. It should be 3 to 5 complete sentences that address the objective or main question of the lab. You should state in the conclusion, in like a single sentence, make a conclusion, and then use supporting sentences to justify and provide evidence for that conclusion based on the stuff you did in your analysis component. This is a place where you can write any trends or patterns you see in the data, describe the relationship you notice between independent and dependent variables, or state your solution to the original lab question, such as what the launch velocity is in my previous example with the physics lab, if it's something like a challenge lab where you have to solve a particular problem. Scrolling down, we have an example of me completing this example lab that we just watched. In the video, we saw a ball being dropped from different heights, and then we were recording the entire time so that we could see the rebound height. So as you go through and look at the video, for instance, there's a part here where I've slowed it down in slow motion, zoomed in, put it in a line, and you can make a measurement from that. I'm helping to indicate what the kind of extremes of the measurement are here between 1.3 and 1.4 meters. And so I go through and I know that this is going to be 1.31, 1.32, 1.34, 5, 6, 7, 8, 1.38 and a half or something. Whatever the measurement is you get from the video, that would be the recorded data that you're going to end up putting in your data table. So we do all that. We make sure we have a diagram in our first component. Notice that I've titled my lab report properly. I got my name, the date, and the name of the lab, which is, you could come up with the name of the lab, or it'll just use the same name that's in the assignment. The diagram here I've decided to sketch myself. You could, again, do this entirely on paper. I'm just drawing it on my computer with my stylus. But I made sure to label all the things in the diagram, right? So I got these whiteboards that are in the background. I've got our 2-meter sticks from the video showing the height markings for where the different drop heights were. Notice this is not like a beautiful artistic rendition. It's not photorealistic. I'm just doing a sketch. I got my bouncy ball in there because that was an important thing. That's the thing we were dropping. And then a camera, which, yeah, that's my camera. because we're filming it, and we're using the camera to actually read the measurements, so that's an important part of the equipment list. So notice I have a diagram and everything is labeled. We get to the procedure. The procedure is just what you had to do, or what I did to collect the data in the experiment. So it's going to be sequential, listed in steps. I've only 6 steps here. I don't think you ever need more than 10 steps. And you'll notice that these are not complete sentences, which is fine. So procedure, I said set up whiteboards and 2 meter sticks vertically against a wall, tape in place if necessary. Indicate drop heights on whiteboards to improve correct drop height when ball is released. That's a good thing to put in, because by drawing those lines where the drop heights were, that made it easier for me to drop it from the correct height, rather than having to go stand right next to the meter stick and block it from the camera view. Step 3, release ball from rest at first drop height. Have camera record in slow motion the rebound height. Step 4, review camera video to see precise rebound height. Record corresponding rebound height to drop height. Using meter sticks as measurement device, record heights in meters. So notice I'm saying, here's the actual recording of the dependent variable, recording the rebound height, using what? That's the measurement tool, the meter sticks, and we're measuring rebound height, that's the thing we're measuring, and then I say the units, we're recording the heights in meters, and we'll see that in my data table. Step 6, I don't need to write this for every drop height, I just say repeat drop procedures for remaining drop heights. You don't have to address how you're analyzing your data, how you're making your graphs in the procedure. Procedure is just about what you did to execute the lab, or what I did to execute the lab in the video, and how data is being collected, with what tools and with what units. Alright, so here's my analysis section, and there are a few different things you could do. So if you're just making a table, you could handwrite your table, or you could put it into a spreadsheet. So I just made a Google Sheets spreadsheet. You could do it in Excel, you could handwrite it, doesn't matter. But I decided to put X and Y to indicate what I'm going to have on the X and Y axes when I eventually make my graph, because in this lab I am going to make a graph. I also indicated which column has the independent variable and which has the dependent, and then I named that quantity, so it's drop height, and I need to put the units in there. So I have parentheses M for meters. Below you see the numbers of the drop heights that we used, and you just put numbers here. You don't put letters in these cells where you put the actual data. You put just write your units in parentheses once at the heading. Then we have the dependent variable on the y-axis, which is rebound height, and then these are the values that I got by looking at the slow motion capture. When we pause the video and zoom in, these are the values that I decided to record based on what I saw. So here's my data table. I could just take a screenshot of that, which is what I did. I just grabbed that, or you could take a screenshot of the whole screen and then crop it later, or you could just write this down on your sheet of paper. And so because I took a screenshot, I just pasted it in there. But you could just handwrite this if you want to. This would be an example. If you just needed a data table, this would be sufficient for the analysis section. This example would require you to also produce a graph. So here's one graph that you could make using Google Sheets or a spreadsheet. I only recommend doing this if you've kind of done it before and you're familiar with it, but there is a way that you can go in and make with Excel or Google Sheets a graph, and it does take a little bit of getting used to, and you have to know how to organize, to customize stuff, and so we're not really going to teach everybody how to do that right now because it's a little excessive. You don't necessarily need to do it, but you can do it this way, and get a graph with a trend line and an equation. You need to title your stuff, but this is sometimes a little more difficult to do if you do it that way. For the physics class, in particular, the Quick Graph 5.0 is a great one to use. You can just put in your data, and then you get a data table, and you have the graph at the same time, and you can select your trend line to fit it, and then it gives you the equation right there. So this is kind of the all-around best way to do it, which is why I recommend that particular graphing application. If you're in physical science, you don't have to worry too much about doing these graphs yet. We're not going that crazy into graphs in physical science yet. You're mostly just going to have a data table that informs your conclusion. Another example, these are all different ways you could do the analysis for this one. Alright, so I have my Excel Google Sheet way with a data table and graph. You can use Quick Graph, or you could go to Desmos, which is another way to do it if you choose to use Desmos for your labs. When you go to the Desmos graphing calculator online, which is very, very useful and a good one to use, make sure you sign in. See, you can click up here to sign into your EBR Schools account so you can save a graph. And if you have your data written in a spreadsheet like this, I can just highlight if I have the X on the left side and Y column on the right side. I just click and drag over, and I can copy or Control C that and go right into Desmos, click in here, paste, or hit Control V if I don't have the option to paste, and it puts my data right in. I can zoom in. I can see it looks pretty linear, it looks line-like. And then if you are interested in using Desmos, then you Google something like how to do a trend line in Desmos, and you can figure that out. Otherwise, just use QuickGraph. But now here I got my trend line. It gives me my slope already in y equals mx plus b format. I got y-intercept and slope 0.7631 if we round it, and in my QuickGraph 0.7631 is also the slope. So you can use these different programs to kind of check your work, but if Desmos is the one you want to try to use, you can paste in your data, you can do a trend line, and you can click the wrench to label your axes. Make sure if you do so you follow the procedures in the physics class that we talked about for using or labeling our axes. It needs to be the quantity and symbol, or like rebound height and drop height don't have particular symbols, so I'm just putting in the quantity and the units. And then you can snap a screenshot of that, or you can click the share button and you can export the image however you want it to be, and you can download that and attach it to your assignment or what have you. Okay, so there you can use Desmos as well. I suggest you pick one of these few things to do, or you could handwrite it. You're not going to want to hand draw a graph, so if you're in the physics class, you're going to want to use one of these methods. I think you would want to use QuickGraph to do the best one. Conclusion is the last component, and this is where we're pulling everything together, addressing the original question or objective by citing evidence from our analysis. So here's what I would write. In this lab, I investigated the relationship between drop height and rebound height for a bouncy ball. I noticed a linear relationship between drop height and rebound height. Namely, for every drop height, the ball rebounded to approximately 76% of the drop height. That's indicated by my slope when I see that in the graph. If I drop it from, zoom in here, if I drop it from 0.5, it doesn't rebound all the way to 0.5 meters. That's what the y-axis indicates my rebound height. So it's rebounding to approximately 76% of 0.5 meters. If I drop it from 1 meter, you can see it doesn't rebound all the way up to 1 meter. That point would be up here. It rebounds to approximately 75% of it. And I know it's about 75, 76% because the slope is what is indicating that. So we need to read our graphs, interpret them, and talk about the actual physical thing that's going on in our conclusion. Some possible reasons, you can go on and make an extension, try to give some thoughts on why the ball might only return to 76% of the drop height. You could think about, if you dropped it from much higher heights, do you expect the trend to stay the same, still be linear, or would it change? I happen to write that some possible reasons why the ball only returns to about 3/4 of the drop height, or about 76% of the drop height. So that's something else you can add into the conclusion. So those are the 4 components. We need to make sure that we have a diagram that is labeled. Everything in the diagram is labeled. Also make sure you title your lab report at the top this way. I've decided to use rows, but you could make quadrants on a single piece of paper if you wanted, or use 2 pieces of paper and write it all down, or do it digitally like I'm doing. Procedure, listed steps, doesn't need to be complete sentences, but listed steps of what was done, and make sure you indicate what things are being measured, rebound height in this case, what is being used to measure it, meter sticks in this case, and then what units that stuff is being measured in. So we only happen to be measuring one quantity here with a meter stick in meters, but you might also have time in seconds that's being measured on a different lab, so you would need to say meter sticks for height in meters and time by a stopwatch in seconds or whatever. Analysis, this is the mathematical or quantitative portion, a number of options you have for completing that, whether it's in a spreadsheet where you do your data, which is either way you should tabulate your data in the spreadsheet. That's a very good thing to do. But you can make your graph other ways. QuickGraph is excellent for that. You could also use Desmos, but you need to pay attention again in the instructions for the lab. Are you told just to do a data table? Are you told to have a data table and a graph? Or are you told to just solve for a particular quantity, in which case you're using some equations that we've been learning in class to solve for, like the first physics lab, the launch velocity of this dart in the Nerf gun. So make sure you look at the directions to see specifically what you need in the analysis portion. I've just given multiple examples here. You would not need to do all like this in Google Sheets and in QuickGraph and in Desmos. No, you pick one or you draw it yourself. And then the conclusion is the conclusion. We just went through that. So those are the components to the lab report. This is the stuff we need to have in there. Your first labs will be coming out soon for you to do, and those will actually be done by video. That's all we got for our example lab report. Till next time, adios.